Namaskar. I am Rudra Kafle from Worcester, Massachusetts. So I am coming with you with a brand new episode of Physics is Fun. It is episode 14th. Okay. So today I will be a kind of extending the applications of Newton's laws of motion. We have started learning Newton's law of motion about 2 months before, since last 2 months, right? So you have already heard about Newton's laws, 3 laws of motion, right? I talked about them, and we are looking into the applications of Newton's second law of motion, right? Just knowing the theory does not help much, right? So you need to apply. When you apply the theory in problems, that will clarify the concepts, okay? So today I am kind of stretching this Newton's second law of motion beyond what we are in general seeing in these presentations, right? So I will be going to do a small demonstration, a very, very simple demonstration, and then I will let you think for a minute or so, and then I will explain the physics behind it using some mathematical equations. Okay, so I would like to ask to have a page like this. Okay, a simple blank paper or any paper which is a kind of flexible like this, right? I have a rolled paper, so please have this kind of paper. Okay, one sheet of paper is enough, right? So so here is the problem. Okay, so please do not do the experiment right away. Okay, what physicists do is predictions, right? So I would like to ask you to predict what happens, right, before you really do the experiment. So if you have a sheet of paper like this, a flexible sheet of paper, right? So it should be flexible like this. You see, it is dropping down, right, like this, right? So what you do is, here is a question for prediction. So do not start the experiment right away, right? So you put this sheet of paper like in front of your chin like this. Please be very careful. The paper may be sharp and it might cut your chin. So please be very careful, right? So you put this way and blow air horizontally, right? Blow air straight horizontally like that, right? So my question for prediction is this. So when you blow air on top of this paper, whether the paper will further go down or will go up or will not change its position, that means it will remain as it is. Let me repeat the question. So this is the a sheet of paper, right? You put right close next to your chin and you blow air horizontally, that means straight ahead, right? Not towards the, not downward or not upward, straight in the front, going to the front, right? So the question for prediction is whether the sheet of paper will go further down or will come straight or upward or will not change. Okay, so I'll give you few seconds to think about this. So please think about this and write comment on your prediction. So please do not do the experiment, right? Once you do the experiment, right, so you will already see what happens, right? But make the predictions, right? So it is a very important physics concept which was discovered in around in the beginning of, like, let's say 18th century. So I'll talk about the physics behind it in a few minutes. Okay, so I hope you did the prediction on this. If you made prediction, what happens, please type in the comment. Okay, so the question was this, right? So you hold this white sheet of paper or any paper, right, which is should be flexible, right, like this. It is flexible, right, like this. So when you blow air over it, blow air over it, so my question was whether it goes further down or remain as it is, or will come up. That was the question, right? So let's do the experiment. Okay? So if you are ready, so let's do experiment together. So I am now blowing air over it. Okay, you saw that. What happened is when I blew air, right, over it, right, instead of it remaining in the same state or falling down, it came up. Okay, so let's do one more time. So you saw that. So this very simple experiment, right, which you can do anywhere in classroom or in a group of students, among a group of students, right, this very simple experiment explains a very, very important principle in Newtonian mechanics, in fluid mechanics, right, called Bernoullis Principle. So this is called Bernoullis Principle, right? I posed a question this morning, right? The question was, in my Facebook status, the question was, so why you are not safe to go very close to the track of a high-speed moving train? Okay, that was the question. And I also saw some of the answers there, right? So those are very good answers, right? So this is a very important principle in physics called Bernoullis Principle, okay? Okay, so let me explain the physics behind it, and then I'll also give more examples where Bernoullis Principle can be used to explain those phenomena, okay? So let me switch my camera to a different mode. Okay, so probably you see my computer screen. I wrote Bernoullis Principle there. This principle was given by Daniel Bernoulli. By the way, Bernoulli was a very elite family. Everyone was highly educated, and some were mathematicians, some were physicists. All right, so you can see the history of them, right? Their biography, right? You can see their biography. But so let me explain. So what happened? In this demonstration, what happened there is we can explain by Bernoullis Principle, which was given by Daniel Bernoulli in 1738, was published in Hydrodynamica. Okay, so what is there? This is the very important equation called Bernoulli's equation. So the first term, okay, the first term here. Let me go show my laser. So the first term here, which is P is pressure. Okay, P is pressure. It has a unit of Newton per squared meter. Newton meter per meter squared. Okay, Newton per meter squared, right? And the second term is rho v square, half rho v square. That is the kinetic energy per unit volume. Okay, that is the kinetic energy per unit volume. In the last class, you saw that the kinetic energy is half mv square. So instead of half mv square, I have written here half rho v square, where rho is a Greek letter, rho, rho is the mass density. What does that mean is rho is mass divided by volume. Okay, mass is in kilogram, volume is in cubic meter. So this is kg per cubic meter, okay, or kg per meter cubed, okay. So in the next factor is v is the speed, right? So that is the kinetic energy per unit volume, and the last term is the potential energy per unit volume. If you remember from the last class, the potential energy is given by mgh. In a gravitational field, if an object has mass m, the acceleration due to gravity of the place is z, and the height of the object above the reference level is h, then the potential energy is m times z times h. So what I have divided on here is I have divided by volume. Okay, so rho gh is potential energy per unit volume. So what Bernoullis equation tells us that the sum of these three quantities remains constant, right? So what does this mean? This means that if pressure increases, if the first term increases, so the second term and third term, either the second term or the third term or both should go down, so that the total remains constant. Okay, let's try to give you a very simple example, right? So suppose I have two baskets, right? I have two baskets. Let's consider three baskets, just like that. And I have 15 apples in three baskets, right? I have 15 apples in three baskets, right? So one has, let's say, 5 apples, next has 5 apples, and the third has 5 apples. The total is 15 apples in three baskets. Now what I do is I move from, let's say, basket 1, I take out one apple and put in the second. So the number of apples in the first basket is less, right? But the number of apples in the second basket is now goes from 5 to 6. So, but the total remains 4 plus 6 plus 5, again 15. Okay, so that's the meaning of this, right? So you can change either of these quantities, either pressure or kinetic energy per unit volume or potential energy per unit volume. But in a system, if you change one quantity, accordingly the other two quantities will change. And interestingly, the total sum of these three quantities remains constant, right? So now let's try to apply that in our demonstration, okay, in our system. So here, so what happened is this is the sheet of paper. I did the demonstration. Let me do one more time, right? So when I blew air over it, right, it came up. So what happened here? When I blew air over it, right, the air over it, the layer of air over it started blowing faster, right? Because I blew the air, right? The speed was higher, right? So the kinetic energy is now higher. Kinetic energy per unit volume, right, is higher here, right? When the speed is higher, kinetic energy per unit volume is higher. And so we are considering the same label. So the last term doesn't change so much. The potential energy per unit volume doesn't change so much in this process. So you can neglect that quantity for now, right? So the kinetic energy per unit volume here, right, in this label, kinetic energy per unit volume in this label, what happens? It increases. So pressure in this region decreases, right? But below this sheet of paper, right, below this sheet of paper, the air is still blowing around. Air molecules are flowing there, but not with that high speed, because above the paper I applied a good amount of force, right? The air speed was particularly really high compared to underneath the paper, right? So what happened now? So the pressure below remains higher, right? So pressure above becomes less, but pressure below becomes high, right? Then it remains high. It remains as it is. But above, it becomes low because of the Bernoullis principle, right? Because the kinetic energy per unit volume is more, so pressure must be less because the total sum should be constant, right? So, but underneath the pressure is high because the air was not flowing that hard, right? So as a result of that, there is difference in pressure. Pressure above is less, pressure below is more. So because of that difference in pressure, that will create force, because by definition, pressure is force per unit area, right? So force per unit area, so force is equal to pressure multiplied by area. So pressure underneath is more, means force underneath is more, which is upward. So pressure over the paper was less, so force was less, so the net force was upward. So as a result of that, the paper moved upward. Okay, this looks a very, very simple principle, a very, very simple demonstration, but it is so powerful. It is so powerful. Let me show you one real example in everyday life. Okay, so you see in this picture, that is a wing of airplane. I took this picture from Wikipedia, right? So this is Airbus A340 wing, right? So it is a wing, like you can see there. I have shown two kinds of arrows here. The arrows on the top there, the arrows on the top show that the air is flowing at a higher speed there. Okay, air is blowing at a higher speed, and underneath this wing, air is blowing at a lower speed. So exactly like that, what demonstration did I do? I did exactly the same way, right? So there is difference in pressure according to Bernoullis principle. The upper part of above the wing of Airbus A340, there was lower pressure, and below that there was a higher pressure. So as a result of that, what happens? The airplane gets a force, very important force, what we call is lift. Okay, that is a lift force, right? So this very, very simple demonstration explain how the lift is how an airplane gets lift in air. Okay, that's very simple demonstration tells us that. So there are other kinds of problems, physics problems, which we can relate with the Bernoullis principle. For example, probably you might have played frisbee, right? So when you play frisbee has a special shape, right? It is like a disc shape, right? So it has a curved shape. So it is designed that way to make aerodynamic. So what happens? To create that pressure difference, right? When it flies, the air blows on the upper side of the upper surface of the frisbee, which is different from the lower surface. As a result of that, the net pressure gives the net force, and as a result of that, there is a lift. In the same way, when you go very close to a high-speed moving train, so what happens? When train moves at a very high speed, so what happens? The air in contact with the wall of the train, right, which is in contact with the wall of the train, has also high speed, right? So as a result of this, there is low pressure very close to the train wall, outer side of the train wall, right? So there is a low pressure, there is a lower pressure. Why? Because velocity is high. So from Bernoullis principle, what we can say that if we consider the same layer of air without considering the change in height, right? So basically we can consider the first two terms in the Bernoullis equation. What does that mean? Pressure plus kinetic energy per unit volume remains constant. So when the kinetic energy per unit volume goes high, so pressure will be low, right? Okay, pressure will be low. So in that region, there is low pressure, but on a little bit farther away, right, the speed of air is less. So as a result, pressure will be high, right, to make the Bernoullis principle true. Okay, so what happens? So because of this situation, there is high pressure a little bit farther, there is low pressure closer to the train. So if someone stands in that particular region, so he or she will, or they will feel a pressure difference. So which, right, as a result of that, there will be inward force toward the train. So it is dangerous of being collapsed in the railway track. So when there is a fast moving train, right, so please be very careful. Don't go very close to the train track when the train is moving at a very high speed for your safety. Okay, the same way, so when two ships or the boats are very close, like moving at a very high speed in water, so there is a very high chance of collision for the same reason. Okay, so probably this helps you to understand somehow about the lift force in airplane, or that simple demonstration which I did, why this flexible paper rises when I blow air on top of that, or some other kinds of problem. Please think about more problems where you can apply Bernoullis principle. They are also used in scientific experiments in lab, where fluids are allowed to flow through narrow tube and wider tube, right? So I am not going to that detail in this episode. With that, I would like to thank you so much. So if you missed previous episodes, I have uploaded those in my YouTube account, so you can watch in there. So please provide your comment. So what like whether you are learning some physics from me, or like if you have any kind of recommendations or to change, or to like, or any kind of feedback from you, they will be very highly appreciated. With that, I would like to thank you so much. Now, as I see in the news that the COVID-19 cases are flaring up in Nepal and in some other countries, so please stay safe, right? So use PPE like mask. Do not go to the crowd. Please stay safe, right? This is going to be bad. Like COVID pandemic is is being bad. So please stay safe. Thank you so much. See you next time. Thank you. Bye.